In the previous video where we were looking at feature importance, I repeated multiple times that it is only valid if our features are independent, right? I mentioned that if the features are independent, only then we can use the absolute value of the weight vectors or the weight values or the weight coefficients, right, as feature importance values, Otherwise, we can't use it. Let's look at why is it so, and let's understand it in slightly more detail. Before we go and understand that, there is a concept called collinearity, which is also called as multi-collinearity, that we need to understand. They're very related concepts that we need to understand. This is one case. This is one of the most important cases where features are not independent and feature weights cannot be used as simple feature importance values, right? Let's see what it means. So let's understand collinearity first. Collinearity is a very, very simple idea. What it means is, imagine if you have two features fi and fj, such that in your whole training data, if you take fi is, let's say, some alpha times fj plus beta, right? Which means if you can get, so for example, if this is, let's say, height and weight, let's just say, if there is some way for me to get the height of a person by multiplying the weight with some constant and adding some constant to it. If this is the case, if this is so, if you have two features which are like this, then if this is the case, then we say that features fi and fj are collinear, right? This is the definition of collinearity. Basically, if you have two features that can be represented in a linear fashion, this is a linear fashion, right? You're representing one feature in terms of the other feature by just using two constants alpha and beta. Similarly, there is a related concept called multi-collinearity. So multi-collinearity is basically collinearity across multiple features. Here we have only two features, right? Fi and fj. What if we have many features? Let's assume we have features f1, f2, f3 and f4. If we have features f1 and f4 such that, right, let's say f1 can be written as alpha 1 times alpha 1 plus alpha 2 f2 plus alpha 3 f3 plus alpha 4 f4, where all alphas are constants, right? If this is so, then f1, f2, f3 and f4 are said to be multicollinear, are said to be multicollinear. So multicollinearity is basically the extension of simple idea of collinearity to multiple features, right? So now you might say, what happens if you have multicollinearity? Why? So the question here is, why does the absolute value of the weight coefficients or the weight vector, right? Why does this not be useful as feature importance if your features are collinear? Right? So the statement I'm making here is, if your features are collinear, then you cannot use the absolute value of the weights corresponding to each feature as feature importance. Let me show that to you with a very, very simple example. Actually, I can argue about this with a very simple example. Imagine I have a data set, right, of xi's and yi's, right? I going from 1 to n. I did all the training and I found a w. Let's just call this w as w star. Let's assume the w is a vector of size 3. This one corresponding to feature 1, corresponding to feature 2, and corresponding to feature 3. Let's assume we have 3 features, right? Now, if you have a query point xq, which has xq1, xq2, and xq3, right? What do I do? I do w star transpose xq, which is what? Which is 1 into xq1, 2 into xq2, plus 3 into xq3. I'm just multiplying this with this, right? W transpose x, this with this, and this with this. This is what your w star transpose xq looks like. Now let's look at it. If feature 2 is 1.5 times feature 1, let's assume, what does this mean? This means f1 and f2 are collinear. If f1 and f2 are collinear, then what happens? I can now use this equation and put it in this as follows. Now I can write w transpose xq as, because xq2 is nothing but 1.5 times xq1. Feature 2 is 1.5 times feature 1, right? So xq1 will remain the same. I will replace xq2 or the feature 2 with 1.5 times xq1. So 2 into 1.5 is 3. So 3 times xq1 plus 3 times xq3. So which will result in 4 times. Now they have 2 xq1s, right? xq1 plus 3 xq1. So I get 4 xq1 plus 3 xq3, which is equal to, what does this imply? Now my weight vector has become 4 corresponding to feature 1, 0 corresponding to feature 2, and 3 corresponding to feature 3. What was the original feature vector? The original feature vector W star that I actually got was 1, 2, 3. But since my features are collinear, okay, this I would get the same result if I had, let's assume I had another W tilde, which is 4, 0, and 3. Now both of these things give me the same classifier. Both of them give me the same classifier because my because my f2 is 1.5 times f1. Both these classifiers give me the same result. Given any xq, they will return me the same value for both of them because of this relationship, right? Which means if features are collinear, my weights can change arbitrarily, right? Now by looking at this first thing, I can say, oh, that my third feature is the most important feature, right? But by looking at this, now I have to declare that my first feature is the most important feature and my second feature is literally useless. If somebody gives you this weight vector W star and some other person gives you W tilde, this second one, your whole results of feature importance will change, right? In this case, you will say that feature 3 is the most important, right? Followed by feature 2, followed by feature 1. In this case, you will say feature 1 is the most important and feature 2 is not at all important. Not at all important because its value is 0, right? You're saying that feature 2 is not at all important. So the conclusions that you arrive at between this W star and W tilde are completely changing, and all of this havoc is happening just because your features are collinear. And hence, by just through the simple example, I have shown you that if features are collinear or multicollinear, right, then your weight vector can change arbitrarily. Yeah, which implies Wj cannot be used as feature importance scores. It cannot be used for feature importance, right? This is the problem. So before we, of course, remember, the world is not perfect. You'll not have perfectly independent features ever. It's almost impossible, right? So one way to determine, so before we use Wj's as feature importance, we want to determine, now given a data set, you have to decide whether you want to use Wj's as feature importance or not, which means you have to determine if your features are multicollinear or not. And how do you do that? Of course, there are many algorithms to determine whether features are multicollinear or not. But the best one that I like is called the perturbation technique, because it's a very, very hands-on technique. It's called the perturbation technique. It's called the perturbation technique to determine whether your features are multicollinear or not. What it does is, suppose you're given this data set, right? Suppose you're given this data set of xi, right? And you have, let's say, f1, f2, fj, so on, fd, right? You have values, you have xij here, and of course correspondingly you have your yi here, you have your class label here. So what it says is, take each of the values of xij and perturbate them. Perturbate basically means to shake it a little. Perturbation basically means to shake it a little. So what you can do here is, for every value of xij, you can add a small epsilon. You can add a small error term or small noise, right? And how can you generate this noise? It's very, very simple. You can generate this epsilon from a random variable with mean 0 and a very, very small variance. For example, you can choose a very small variance like this, Okay, like maybe 0.1, let's say 0.1. Okay, this is your mean and this is your variance. So you can basically, for every value in this matrix, you can simply add a small noise term. When you add a small noise term, you're perturbating each of these values slightly. Remember, you've already column standardized all this. You've already column standardized all this data. Now you're adding a small error or small noise. Now what you have to do here is, before you add your noise, you compute your W. Right? Before you add your noise, so right, Wj, so on and so forth, Wd. Okay, before perturbation. Before perturbation, you compute your weight vector. And after perturbation, again train your logistic regression, compute your W tilde. So W1 tilde, W2 tilde, so on, Wj tilde, so on, so forth, Wd. Right? Now, if these two values differ, drastically, then you can conclude, if these values differ, if Wi and Wi tilde differ significantly, if they differ significantly, small changes are okay. If they differ significantly, then you can conclude that your data, that your features are collinear. When they are collinear, what you have to do? Then you can't use Wj's as feature importance values anymore. But if they don't differ much, they differ slightly, let's say. If they differ slightly, then you can continue to use your Wj's as feature importance score. So cannot use, sorry. Okay, if they differ significantly, this is important. If they differ significantly. So what are we literally doing? We are saying, given our training data, we'll train one model, we'll get our weight vector. Let's perturbate this slightly. By adding a small noise, I'm getting a new model. If these two models don't change significantly, then yes, then probably, again, none of these tests are perfect. Perturbation tests is a very interesting test that I personally like. There are like at least 10-15 tests that I've heard of to detect multi-collinearity. None of them are like perfectly perfect, but they give you a sense of how bad the situation is, right? So remember, you should always check for multi-collinearity or collinearity in your dataset before you start using your Wj's as feature importance values, your absolute value of Wj's as feature importance. If you do not do the multi-collinearity check, you could really come to disastrous conclusions. I have seen cases in my own experience where people do not check for multi-collinearity. And say, this feature important, this feature is not important. But the moment you do a test like perturbation test, you quickly notice that there is so much multi-collinearity that you simply can't use the absolute values of Wj's as feature importance anymore. So it's important to note that. And when you can't use Wj's as absolute values of feature importance, we always have our forward feature selection technique, right? Right? This can be used for any model. This is what we learned when we learned k-nearest neighbor to understand feature importance, right? So this is something that we can continue to use here. But if you don't have the problem of collinearity, then you can directly use the weights corresponding to each feature as feature importance.